Hello friends, in our previous video we have seen the voltage regulator, that is series voltage regulator based on BJT or BJT based series voltage regulator. Here in this video we will be talking about series voltage regulator using Opamp. This is the circuit diagram of series voltage regulator using an Opamp. This is series element, which is nothing but series pass transistor, and this is a comparator circuit. This is comparator where we have a voltage at input Vz and we have the voltage feedback, that is Vx. This is your feedback voltage, right? So ideally for ideal op-amp, voltage at non-inverting terminal is same as voltage at inverting terminal. Here voltage at non-inverting terminal is Vf and that is same as voltage at non-inverting terminal, which is Vz. Now you please see carefully, the voltage Vf, voltage across this resistance will be what? That is, you simply apply voltage divider rule, R1 divided by R1 plus Rf multiplied by output voltage. You please see, this resistance divided by sum of 2 multiplied by output voltage is this voltage. Either you can say feedback voltage or you can say Vx, that is same thing, right? So I will denote it by Vx, that is voltage at node x, rather than, because in text I have taken like that only. Fine. So you know what is Vx? Vx is equal to Vz. So this gives output voltage V out equal to R1 plus Rf divided by R1 into Vz. So output voltage of this circuit V out will be equal to, that is 1 plus Rf by R1 multiplied by Vz. This is the output voltage of this circuit, which is very important from examination point of view. There can be question, there can be numerical based on this. Now let us understand the operation of the circuit. Suppose my output voltage changes because of the any reason. The output voltage can change because of the change in load resistance or because of the change in supply voltage. In this case we will be talking about these two only. This is your control element, this is comparator, this is feedback arrangement, this is reference voltage. Vz is reference voltage because that is constant. Now suppose I want suppose there is change in output voltage, either, or suppose there is a reduction, I will say suppose there is a reduction in output voltage. Output voltage can reduce because of what? Let us see, because of reduction in the load resistance or maybe because of the reduction in the supply voltage. So suppose output voltage is reduced. When output voltage is reduced, please see carefully, the voltage across R1 will be reduced. Why? Because voltage across R1 is Vx. So if it is reduced, then Vx is also reduced. If output voltage is reduced, your Vx is also reduced. When Vx is reduced, voltage at terminal B becomes less than the voltage at terminal A. Voltage at non-inverting terminal becomes more, voltage at inverting terminal becomes more, voltage at non-inverting, I'm sorry, there is a little change here, this is plus, this is minus. So it has to be like that. So if your output voltage reduces, the voltage across resistance R1 is reduced, and if voltage at R1 is voltage across R1 is reduced, that means voltage at inverting terminal is reduced. Voltage at non-inverting terminal is constant. So if voltage at non-inverting terminal is constant, voltage at inverting terminal is reduced. So the differential input voltage, which is Vd, what is differential input voltage of this circuit? That is Vz minus Vx. So that means if voltage at inverting terminal is reduced, voltage at non-inverting terminal is constant, so the voltage differential input voltage will be increased. So with reduction in Vx, Vd is increased. and if Vd is increased, the voltage at output terminal of op-amp is increased, and if voltage at output terminal of op-amp is increased, your BJT will be driven more. It means base current is increased, right? So if voltage at base terminal is increased, you please see carefully, if voltage at base terminal is increased, your BJT is driven more, means collector current will be increasing. If collector current is increased, please see carefully, if this is increased and this is reduced, so VBE, please see, VBE is what? Output of op-amp minus voltage, output voltage. If this is reduced, this is increased, so VBE will be increased. I can say like that. So the voltage across base ammeter junction will be increased if your output voltage is reduced. In other words, when output voltage reduces, the voltage across base ammeter junction increases, and we know the collector current of BJT is what? The collector current of BJT is given by, that is saturation current into e raised to power VBE by Vt. So if voltage VB is increased, in that case collector current will be increased, and if collector current is increased, this is collector current, in that case ammeter current will be increased, your load current will be increased, and if load current increases, your voltage across the load will increase. So the voltage across the load which reduced because of reduction in load resistance will be pushed up due to this feedback mechanism through op-amp. In other words, voltage will be maintained at constant level. It reduced because of reduction in load resistance, but it increased because of this feedback mechanism due to increase in base to ammeter voltage, due to increase in collector current, due to increase in load current. Take another case. Suppose your load voltage is increased. How it can increase? Either because of increase in supply voltage or because of increase in load resistance. So suppose voltage across load is increased. If voltage across load is increased, that means V output is increased, your voltage at node X will increase. If voltage at node X is increased, your differential input voltage will reduce. Why? Because voltage at node X is increased, so this will, overall difference will reduce. And if Vd is reduced, voltage at output of op-amp is reduced. So please see, if voltage at output of op-amp is reduced, V out was increased, so VBE will reduce. And if VB is reduced, what will happen? My collector current will reduce. And if collector current reduces, your ammeter current is reduced, load current is reduced, and if load current is reduced, output voltage is reduced. It means the output voltage which increased due to increase in load resistance will be pulled down because of reduction in load current, because of this feedback mechanism. So that will be brought back, and that is how the voltage at output terminal of op-amp will be maintained at constant level. I hope concept is clear, and if it is not clear, you please rewind your video, see it again, you will understand it. Fine. So now let us see the power dissipation of this circuit. What is power dissipation? The power dissipation is because of the BJT which is connected in series, and that is called series pass transistor. BJT, the full load current of the supply will be, or full load current of the regulator will be passing through the BJT, and that results into the power dissipation in the regulator. So power dissipation of this regulator is because of this series connected BJT. And here BJT is used as an amplifier, and in amplifier collector junction is reverse biased, and because of reverse bias collector junction there will be heat dissipation at collector junction, which will be heat dissipation of this power supply. So the heat dissipation of series voltage regulator using op-amp is nothing but voltage VCE into collector current, and voltage VC is what? Input voltage minus output voltage into collector current. And you know what is collector current? Collector current is same as base, that is ammeter current minus base current, and that is beta by 1 plus beta into what? That is, I'll repeat, my collector current is same as, that is what, beta by 1 plus beta multiplied by ammeter current. And you know what is ammeter current? Ammeter current is same as feedback current plus load current. So my collector current here will be equal to beta by 1 plus beta multiplied by feedback current into IL. Or what is feedback current? Feedback current is V out upon R1 plus R2. So by putting this expression here, you can get collector current, and by putting collector current here, you get power dissipation in the power supply. There can be numerical on this, so see it carefully. You have question based on power dissipation in series voltage regulators. So that covers your series voltage regulator using Opamp. Here remember, the peak of supply voltage should always be, peak of input supply voltage should always less than the Opamp rating, right? So power supply rating of the Opamp, you can say, and minimum input voltage is greater than or equal to output voltage plus 2 volt to keep Opamp in saturation. Your Opamp should be working in saturation mode. Opamp is not being used as an amplifier. Opamp is being used as a comparator, where your in comparator Opamp works in saturated mode. So Opamp should be working in saturation mode, and beta of the transistor should be large, and BJT must be able to dissipate how much power? That is, if your IC, you can please see carefully, IC can be approximately equal to IL, so minimum this much power must be dissipated, that is rated current. So V out into IL must be the minimum power dissipation which we should be able to do in BJT. So these are some of the points related to series voltage regulator using Opamp. But this is very important from examination point of view. There are lot of questions in GATE instrumentation, GATE electronics engineering from series voltage regulator, especially series voltage regulator based on Opamp. Now we will see the examples which appeared in GATE in past, and before we proceed to the next topic, that is shunt voltage regulator. Let us take example on series voltage regulator based on Opamp now. We have the statement linked on questions here. A regulated power supply shown in the figure below has unregulated input of 15 volts and generates a regulated output V out. Use the component values as shown in the figure, and ground is shown by the symbol. This is ground, right? So the power dissipated across the transistor Q1 shown in the figure is, first we have to find the power dissipated in the transistor. So remember, voltage across BJT here, voltage across the BJT in the circuit is VCE. This is VCE, and collector current is IC, suppose. So the power dissipated in the BJT is given by voltage VCE multiplied by the collector current, right? And voltage VCE here is nothing but V input minus V output. So input voltage here is 15 volt. We need to find output voltage. Remember, say this is node X for ideal Opamp. Say this is node X for ideal Opamp. Voltage at non-inverting terminal is V plus and voltage at inverting terminal is V minus. So for ideal Opamp, V plus is equal to V minus, and that is equal to, or we can say what is V plus, that is Vz. Voltage across the general diode is how much? Vz. So Vz is equal to Vx. And what is voltage at node X? This is nothing but voltage across this resistance. You can write this in terms of output voltage. Current in this circuit is 0. Current here is 0 for ideal Opamp. So whatever is voltage across this, that can be obtained in terms of output voltage, and that is nothing but 24. You simply apply voltage divider rule. 24 divided by 24 plus 12 multiplied by output voltage, right? So what will be output voltage? The output voltage can be written in terms of general voltage like 1 plus 12 divided by 24 multiplied by output voltage, which is multiplied by Vz, which is how much? This gives 1.5 multiplied by Vz is 6 volt, that is given here. So this is equal to 9 volt. So voltage VCE in the circuit will be 15, you can see here 15 minus 9 volt, so that is 6 volt. So we have obtained input voltage across BJT. Now let us find out the current. First of all, there are two components of current in ammeter or terminal of BJT, that is, one is load current and second component of current is in this branch. So load current IL is nothing but V out by load resistance RL. So that is 9 volt is output, load resistance is 10. So this is 0.9 ampere. Current I will be what? Current I will be V out divided by resistance, say 12K plus 24K, that many milliampere, or that is 9 by 36, that many milliampere, or you can see this is nothing but 0.25 milliampere, which is very small in comparison to this. So ammeter current of BJT will be equal to the load current plus I. Why? Because ammeter current is this current in this branch, and current in this branch will be ammeter current, and that is equal to 0.9 ampere plus 0.25 milliampere. So this is in ampere, this is in milliampere, so this will be approximately equal to 0.9 ampere. The base current of BJT is suppose IB, so collector current of BJT will be the ammeter current minus base current, and base current is negligible in comparison to ammeter current of BJT. So this is approximately equal to IE, which is 0.9 ampere. So the power dissipated will be equal to how much? That is 6 multiplied by 0.9. So that gives you 5.4 watt. 5.4 watt. Answer is C. That is first part of the question. Let us see second part. If unregulated voltage is increased by 20%, the power dissipation across the transistor will be, right? So you have to find the power dissipated if input supply is increased. So input supplied after increase of 20% will be how much? 1.2 multiplied by actual input voltage, which was 15, right? So this is 18 volt. So if input voltage is 18 volt, then what will be VCE? VCE will be V in minus V out. V out will remain constant. So 18 minus 9 volts, so that is 9 volt. VCE will be 9 volts. So power dissipated in the BJT will become, that is new value of VCE multiplied by IC. So that is 9 volt multiplied by IC is how much? 0.9. So that gives you 8.1 watt. So what will be the percentage change in power? Percentage change in power. Say this is PD2. So say this is PD1 now, right? So percentage change in power dissipation will be what? That will be, yes, that can be written like PD2 minus PD1 divided by PD1 multiplied by 100. So that is 8.1 minus 5.4 divided by 5.4 multiplied by 100. So power dissipation has increased, and this will be equal to how much? This will be approximately equal to, you can calculate that, that will be approximately equal to 50%, right? So this is your answer. Fine. So that is the question based on or example based on series voltage regulator with Opamp. Now let us see next example. Let us see next example now. For the voltage regulated circuit shown, the input voltage Vm is 20 plus minus 20%. The regulated output V out is 10 volt. Assume the op-amp is ideal. For the load RL drawing 200 milliampere, the maximum power dissipation in transistor is. So power dissipated in the transistor, suppose voltage across transistor is VC, collector current is IC. The power dissipation in the transistor is given by what? Voltage VCE multiplied by current IC, where VCE is equal to input voltage minus output voltage. Now for maximum power dissipation we need to take VCE max, so I need to take V in max, right? So input voltage maximum will be how much? 20 plus 20%, and that is nothing but 0.2 into 20% of 20 volt. So that is how much? This will be 24 volt. So the voltage VCE maximum will be equal to how much? Input voltage of 24 volt minus output voltage of 10, so that is 14 volt VC max, right? Now we need to find what is load current. Load current IL is approximately equal to, or that is given to you, load current is 200 milliampere, right? Now R1 is not given to you, but say this current is I, so ammeter current is how much? Ammeter current of BJT, that is ammeter current of BJT is this. Ammeter current of BJT is equal to current I plus load current, and this is approximately equal to load current, which is 200 milliampere, which is nothing but 0.2 ampere. So the collector current of BJT will be equal to what? Base current, ammeter current minus base current, and base current is here, that is base current is negligible, and this is approximately equal to ammeter current. These are approximation we commonly use, and this is equal to 0.2 ampere. Then what will be power dissipation? That will be maximum power dissipation, you can say, that will be VCE max into IC. This is equal to VCE max is how much? 14 volt, and IC is what? 0.2, so that gives you 2.8 watt. So 2.8 is between 2.7 and 2.9. Let us see next example based on series voltage regulated with op-amp. The output voltage of regulated power supply shown in the figure is. You have to find output voltage of this circuit. Remember, for ideal op-amp, V plus is equal to what? V minus. So what will be V minus here? V plus, and V plus is how much? V plus means voltage at non-inverting terminal, V minus means voltage at inverting terminal. So for ideal op-amp, this is for an ideal op-amp. So this is assumed that op-amp here is ideal. So V plus is what? V plus is Vz, and here V plus is Vz here, and that is how much? That is equal to 3 volt. So voltage at inverting terminal is nothing but Vz, and that is 3 volt. But if in terms of output voltage, if voltage here is V out, so you can write V minus in terms of output voltage, that will be 20 kilo ohm divided by 20 plus 40 kilo ohms multiplied by V out. So what I did, output voltage across this is nothing but V minus, and total voltage is V out. So by simply applying voltage divider rule, because current, remember current in inverting terminal is 0, so voltage across this is simple part of the output voltage. So you can find voltage across this resistance is V minus, which will be this resistance divided by sum of 2 multiplied by output voltage. So this is 1 by 3 multiplied by output voltage V out, or V out will be 3 times V minus, and V minus we have already written, so that is 3 multiplied by 3, that is 9 volt. So answer is C, and that finishes the examples based on op-amp based series voltage regulator. Now in next video we will be talking about shunt voltage regulator. So wait for my next video. Thank you very much for watching the video.
To watch more videos like this, Subscribe. Click on the bell to turn on notifications. Click on the like button. Share.